Hello students. We're going to take the next step in our analysis of two variable relationships. So far you have learned how to look at the relationship in a scatter plot to get an idea if the two variables are related and how are they related. Then we also learned a way to measure the relationship, the strength and direction of that linear relationship, and that is the correlation coefficient. Now we're going to move into fitting the line, the best possible line that would represent the model of our data. Then we could use that model to make predictions among other things. Here's an example. Here's a scatter plot. I could move this line to what I think would be the line that would represent this data well. Does it have to be the same amount of points above and below? No, that's a common misconception that some students think. It has to represent the data the best, it has to fit the data the best, but what does that exactly mean when we say line of best fit? Would this line be the line of best fit? Would this line be the line of best fit? Would this line be the line of best fit? Well, there is one answer, and we are going to use the least squares regression model. Least squares. What that means is we are going to first show a residual. We're going to first, in other words, draw a vertical line, a distance from each point to our so-called line of best fit. These are called residuals. This basically is our errors, this is where our line is not perfectly a perfect model, because as you can see, the model, the line, would predict the y value to be here. The actual value is here. So these are the residuals. If we square these residuals, we can now add up all these squares, and we have one large area. The line of best fit, then, is the line that we would place that would minimize the sum of these squares. So as you can see, if I play around with this line, some of the squares are decreasing in size, some are increasing. So there's give and take here. So where could I put this line that would minimize the sum of all the squares? Well, this website can do that. I'm going to show the line, and there it is. That line right there apparently minimizes all the squares, the sum of them. We can show the actual value, 31, is the sum of all the squares. And I think I was probably more in the ballpark of maybe 40 or upper 30s. But the line of best fit, again, would be that. And that's the least we could make those squares given our data set. And there's your definition of the line of best fit. Least squares of the residuals. Now it's a model. It describes how the y variable changes as the x variable changes. And yes, you remember from algebra the equation of a line. You probably learned it, y equals mx plus b. It doesn't really matter what letters you use. Like here we have an a for the slope. What's important is you know that the letter that is next to the x variable is the slope. I could put an m here, I could put a b here, I could put an a there like there is. Either way, whatever next to the x is the slope, and the number out here by itself is the y-intercept. Here's an example. Some data was collected for many men over the span of many years, and they recorded when they started exercising. Now, assuming they continued to exercise, they followed them to death. And they, out of the whole group of men who started exercising at age 37, they lived an extra 2.5 years compared to other men who did not start exercising. Now, as the men started later, they still gained life, because exercising overall should help, but the amount of life they gained did decrease as they started later. So if you start exercising at the ripe age of 77, you still, it looks like, can, on average, gain an extra half year of life. Now, we can use technology to calculate that line of best fit for us, and here it is. But what you guys have to be able to do is interpret this line. Specifically, interpret this slope right here. And here's how we're going to do it. As the x's increase, this is the x variable, remember. As the x values increase, or using context, we would say, for every year one waits to start exercising, that's the same as saying as the x values increase, they can expect to lose 0.05 years of additional life. Now, I got the 0.05. Well, I got the negative. I got the lose from the negative sign. As the x's increase, this line's going to go downhill. As x's go to the right, the line's going to go downhill because of this negative slope. Now, that might sound counterintuitive to gaining life, but remember, what we're looking at here is they are not gaining as much life. The amount of life they are gaining is decreasing as they start exercising later. And I rounded the 0.0503 just to 0.05. Notice when we're interpreting slope, we don't really have to use the 4.53 in the interpretation because that is a set number. We're going to start there on the y-axis, but from each value of x we move, the y is going to move this much. So you only have to interpret the slope when you're asked to interpret the slope. Let's try it again. We have a company that recorded how many thousands of dollars they spent on advertising in a given year, and what were their sales for that given year. Here is the equation of the line of best fit, and you can try this yourself. You can pause the video and see if you could fill in these two blanks here. Okay, for every extra $1,000 spent on advertising. Now, where do I get that? Well, look at your units. Each of these are in 1,000s of dollars. So as each x goes up by 1,000, which would be 1 on this scale, we can expect an increase, because this is a positive slope now. There's no negative sign here. We can expect an increase of 49.5, which again is in thousands. So we can expect an increase of $49,500 in sales. Keep in mind, this is just a model. So if a company spends this much extra on advertising, they can't guarantee they're going to make that much more in sales. But the data does suggest that that may happen on average. All right, now if our scatter plot looks pretty linear and correlation coefficient is pretty strong, closer to 1 or -1, we can make useful predictions into the future, kind of like having a crystal ball. All right, so here's the exercise and additional life equation. What if we start exercising at the age of 40? This is where now you just simply plug in your 40 for x, because exercising is the x variable, and we just have to calculate with these numbers, and the y hat will be our predicted years of extra life. So it looks like that. You multiply it by the 40 first, and then you do add the 4.53, and we can expect to add about 2.5 years of additional life if we start exercising at the age of 40, based on data. What about starting to exercise at the age of 4? Maybe we can plug the 4 in and see how much more life we could gain. Well, I'm telling you not to bother, because we call that extrapolating too far outside of our data range. You can't really trust your results unless you plug in numbers that are fairly close to your collected data. We didn't start collecting data on these men until they were 37 years old and above. So starting at exercise 4, or at age 4, we could not trust that result. Finally, how confident can we be in making these predictions? 3 key things to look at. Look at the scatter plot. Is a line a good model, or do you see curvature? which would make predictions not as good using a linear model. So do you see a line when the data lines up? 2, is your R and R squared, we'll talk about R squared in a minute, are they fairly strong to at least a moderate relationship? If they're weak, that's and the scatter plot is scattered, then we can't really trust our prediction. Finally, make sure we don't extrapolate. Make sure we make predictions that are within our data range or close to the edges of our data. Then we can check off and say, good, we can count on our prediction. And finally, R squared. What is R squared? Well, it's similar to R. It tells you how strong of a relationship you have. It does actually tell you a little bit more. It tells you the percent of the variation in your Y's that can be accounted for by the changes in your X values. It's a percentage. It's only between 0 and 1. And as the linear relationship gets stronger, it gets closer to 1. If we look back at this example, I have the R squared calculated for this example. It's 0.6 or 60%. Here's how we would interpret that. We would say for every we would say for each, not for every, let me correct that. We would say 60% of the variation in our additional life added can be accounted for by its linear relationship to age starting exercise. You might want to rewind that, listen to that again, and thanks for watching. Good luck. See you soon.